So welcome to my channel on technology space with machine learning and artificial intelligence. So the today's topic is ship underactuation. This is the part one of a two-part series, and this presentation also part of this maritime technology playlist. So let me elaborate why this is an important topic in shipping. When we are applying advanced controllers into ocean-going vessels, the vessel actuation or the capabilities of rudder propulsion thruster systems to control these vessels under various weather conditions should be understood. Otherwise, the controllers we are going to apply into these type of systems will not achieve the stability or the robustness that we are expecting from these applications. So in the robotics community, generally these researchers are studying under fully actuated robotics as well as the underactuated robotics. Since most of the control theories and applications been in the robotics community been adopted also towards the shipping industry, I think understanding these underactuated conditions of these systems is really useful. I would even think majority of these ship controllability situations or the controllers we are developing towards these vessels should facilitate these underactuated systems, because most of the vessels or the majority of the vessels can be considered as underactuated system. However, I would explain what is this underactuation and then how that is going to applicable towards these ocean-going vessels in the following slides. So let's try to start this discussion from the basics. So here a rigid body is an equilibrium. That means the rigid body is laying in a frictionless surface, and it has the mass of m, which is denoted by m. So why we are considering this frictionless surface? That means if someone is trying to push this rigid body throughout the table, there will not be any friction force going against that rigid body motion. So the mass distribution in this rigid body is fixed. So the center of gravity, which I denoted in this figure as CG, is the average location of the weight, and this center of gravity also fixed. As you can see in this figure, since this rigid body is laying on that frictionless table, the weight is acting on that center of gravity towards the table. So the table is working against the weight of this rigid body. Because of that reason, the rigid body is in an equilibrium conditions. So in the future slides, what we're trying to do is applying forces into this rigid body and see how this rigid body could respond to such forces. So in the first step, we would apply an external force along the line which intercept that center of gravity of the rigid body, and see what could happen to the rigid body itself. So what could happen when we are applying a force going across this center of gravity of the rigid body? This rigid body will achieve an acceleration. So this acceleration is denoted by AT. So there's a relationship between the force, mass, and the acceleration, which is this F equal to ma. That means the applied force equal to the mass times the acceleration that the rigid body has achieved in this situation. So if you're applying another force which is not going across the center of gravity of this rigid body, but this applied force direction has a perpendicular distance d from the center of gravity of this rigid body. So what could happen in such type of a situation? So obviously the first thing could happen, since this force is applying on the rigid body itself, the rigid body will achieve an acceleration. In this case, I am introducing this wording of translational acceleration. So if you're interested in more details on these translational and rotational motions, I would place a link of a previous video, and please go through with that, then you would get a better understanding on this translational and rotational acceleration. Anyway, in this case, I am denoting AT as the translational acceleration achieved by this rigid body due to this external force F. So the first effect due to this external force on the rigid body we have discussed in the previous slide. That means the rigid body has achieved that translational acceleration of AT. That means it start moving into the same direction of this translational acceleration. So the second achievement would be the rigid body will have this movement m. So that movement equal to the force times the perpendicular distance to that force. So then due to this moment created by this force, the rigid body will have an angular acceleration or the rotational acceleration, which is denoted by AR in this situation. So that means the rigid body start to rotate itself around the center of gravity and have width under this acceleration AR. So that means it start rotating around the center of gravity at this point. So if you combine both translational and rotational accelerations, so then the motion of this rigid body would be it start moving into this translational acceleration direction, and the same time it is rotating around its center of gravity. So this motion somewhat complex in this situation for this rigid body. So then the next question would be, how can we make that rigid body come to an equilibrium situation? So the concept we should implement this case was if a rigid body in an equilibrium condition, so the net force as well as the net moment about any arbitrary point in this rigid body should be equal to 0. So let's try to pick arbitrary point and then try to see how can we make the net force as well as the net moment around on this rigid body goes to 0. So as the first step, let's pick an arbitrary point in this rigid body. So the point is selected as A in this situation. So then since we have to make that net force in this rigid body equal to 0, we have horizontal force coming as F1. Let's try to create an horizontal force F2 which is equal to F1 but into the opposite direction of F1. So at this point the net force in this rigid body equal to 0. So what that could be resulted in the future. So when the net forces in this rigid body equal to 0, that would be resulted in 0 translational acceleration. So as you have noted, the translational acceleration of AT equal to 0. So that doesn't mean this rigid body is in equilibrium condition at this point. So that means after applying this force F2 which is equal to F1 but in a opposite direction, this rigid body still start to rotate around its center of gravity due to these movements. So let's try to see how can we stop that rotational motion also in that rigid body. So the second step would be we have to make that net moment around the rigid body is equal to 0 around this arbitrary point. So let's apply a moment called M2 which is also equal to the M1 but in the opposite direction. So now we can imagine this is the second step we should take to make this rigid body come to an equilibrium condition. So what we did previous step, we have applied M2 moment around this arbitrary point which is equal to the M1 but having an opposite direction. So as a result of that moment, opposite moment of the existing moment, the moment will get cancelled out. So therefore the rotational acceleration which is AR will be equal to 0. So since what we have done so far, we have applied equal and opposite forces, force and a moment into this rigid body to cancel its existing force and the moment. So that way the net force also the net moment in this rigid body becomes 0. So due to these force and moments equal to 0 situation, both rotational and translational accelerations also become 0. So that means this rigid body came into an equilibrium situation. So what we did previous step was we have applied equal and opposite force and moment by considering the existing force and moment in the rigid body. That way that rigid body came into an equilibrium position or equilibrium condition. So let's think about a situation. We are applying a opposite force into the same arbitrary point A, but this time this opposite force F2 is less than F1. So what that could be resulted in? So you probably know when you apply two forces which is opposite to each other, so there will be resultant force, which is the larger force minus the smaller force. So there will be resultant force in this situation also. That would equal to F1 minus F2. So that means there will be a resultant force acting on this rigid body at this point. So what that could be resulted in? So as you have noted in this figure, due to that resultant force, there will be acceleration in this rigid body, which is noted as AT in this situation. So since there's a resultant force, this acceleration will not be equal to 0. Because of that, I have noted that as AT greater than 0 in this situation. So that means this rigid body start to move into the start moving itself into the same direction as that resultant force or the resultant acceleration. So let's think about the situation. We are applying a moment M2 into the same arbitrary point, but similarly in this situation also this M2 is less than the existing moment of N1. So that means there will be a resultant moment in this rigid body. So due to that resultant moment in this rigid body, which is equal to M1 minus M2, there will be rotational acceleration will also be in that rigid body. In that this rotational acceleration is denoted by AR in this figure, and then I have also mentioned AR is greater than 0. That means this rotational acceleration is not equal to 0 due to this resultant movement in this rigid body. So let's try to summarize what we have discussed so far. There was a rigid body laying in that frictionless table. Then we have applied this external force F1. As a result of that external force, this rigid body start to move one direction as well as start to rotate around its center of gravity. This is due to the force F1 has created this translational acceleration, and then the moment M1 has created this rotational acceleration. Then we have discussed how can we make this rigid body come to an equilibrium situation. So what we did was we picked an arbitrary point and then we applied equal and opposite force and moment by considering the existing force and moment in this rigid body. So if you had an equal force and moment into an arbitrary point, what happened in this situation was the rigid body came into an equilibrium position by having both translational and rotational acceleration goes to 0. But in the second case, we pick this arbitrary point, then we assume that we would not be able to create strong force and moment, which can counter the existing force and moment in this rigid body. What could happen in such situation? So due to this force imbalance, there would be a resultant force. Similarly, due to this moment imbalance, there would be a resultant moment. So as a result of that, the rigid body rigid body can have a translational acceleration as well as rotational acceleration in this situation. So let me say some additional points with respect to this slide. Can you think this rigid body as a system, and this arbitrary point is where you have two actuators. One actuator can create external forces and the other actuator can create movements. So think about this. F1 is an external force influencing this system, and then you want to counter this force and the movement effect due to this external force F1. So you need two actuators which can create enough force and movements to encounter that external force. And think about a situation, you actuators may not have enough power to produce the force and the movement it required to encounter that existing force and the movement. So in such situation, the system would fail to control itself. So that is the situation I'm going to describe in the future as underactuated situation. So we have assumed that the rigid body is a system and then its actuation powers are located in this arbitrary point A1. So the actuation power means the system would be able to create required force as well as required movement. So the fully actuated system can be defined as a system that can execute commands given by on its motion, especially by the controllers due to sufficient actuation power. If you remember in the first example, we have discussed that this arbitrary point can create force and movement which can encounter the existing force and movement in this rigid body. That way we were able to control this rigid body into an equilibrium condition by having both translational and rotational motions, accelerations goes to zero. So such type of situation or such type of a system can be categorized as a fully actuated system. But there can be underactuated systems. So simply that means that the actuation power created in this point A would not strong enough to counter that existing force and moments in this rigid body or in this system. So that was the example we have discussed in the second part of this presentation. So the underactuated system can be defined as a system that cannot execute commands by on its motion, probably given by these controllers due to insufficient actuation power. So that was the second example we have discussed in this presentation. So now the next step would be to describe ship underactuation based on this rigid body motion. Let's assume that the rigid body is the vessel and this frictionless surface is its navigation waters. So let's try to see how these underactuated conditions in the rigid body can also be utilized to explain the underactuated conditions in these ocean-going vessels. So let's discuss that in the second part of this video. So that's the end of this presentation. Hopefully you have enjoyed that. So additional related information and updates on this video would be in the description of this video. So if you are still interested in this material, please stick around. Thank you.